Lesson 100 is very much an in-class activity, but I'm going to do my best to describe what's happening, but you might want to talk to your teacher about it if you were not in class. So it says, you've learned about the importance of choosing a sample randomly so that the sample represents the population. If a sample is chosen with good methods, it is still possible for the data from the sample to be different than the data. Is it still possible for the data from the sample to be different from the data from the entire population? If it is possible, how can we ever make any decisions from sample data? This is a question we will be answering throughout the rest of the unit. So the idea here is if I have a population, which we'll draw with a circle, and I pick a sample, and even if it's random, like I randomly pick, different values, there's still a chance that I happen to pick values that are in general have a higher number than the population or a lower number, because there's always, even in randomness, we're never quite sure if we're representing the population. So there's, we say that these are differences due to randomness, not necessarily bias or something like that. So we have to come up with a way. It's not like we can say, well, that means we can never use samples. We have to come up with a way where we can still make decisions, even in that face of uncertainty about if our sample is perfect for the population. So what in class, each person's going to be given a little baggie of colored chips. Really, they're just circles of paper. The population of chips is 40% peach, or 0.40. So there's yellow and peach. 40% of the little circles in there are peach, and 60% are yellow. So each person is going to randomly select a sample chip without looking from their container or baggie, and then they're going to record its color. So they'll have peach or yellow. So maybe the first one they pick is yellow, and then they get yellow and peach, and then yellow and peach and peach, yellow, 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 peach. Go back to tallies, yellow, peach, yellow, yellow. Make that 4, like I said. Yellow, peach, peach, yellow, yellow, yellow. Okay. So after picking 20, and each time you put it back in and you pick a new one, the number of peach chips in your sample was 7. So the proportion of peach chips here, we have 7 out of 20. The sample was 20, which is 0.35. So we call that a sample proportion. It means 35% of the chips we picked were peach. Okay. Now, in class, people are going to have Post-it notes, and they're going to write their sample proportion on it. So that person would write 0.035, and then they bring it up to the board where we have a number line, and they put it on just like we put an X on a dot plot, or a dot on a dot plot. And the whole class is doing that. They'll do it a couple times, and we're going to get this distribution like the 2 lessons ago when we had those dot plots or histograms and things like that. So down here it says place your note above the value on the number line that corresponds to your sample proportion. So this person would put it above 0.35. The graph of all the students' sample proportions displays the sampling distribution of sample proportions. So it's called a sampling distribution, this resulting graph. This sampling distribution can be used to determine if other samples from other populations could have a value of, and I should say, 0.40, because that's what this population has. We know the whole population of peach chips, or the whole population has 40% peach. So I'm going to scroll down, and let's just pretend this is the graph we got for your class. So here, 3 people got their proportion was 0.25, 6 people got 0.30, 10 people got 0.35, 7.40, and so on. So each Post-it in the distribution. So I have X's, but really these are like little Post-its up on the board. That represents the proportion from one sample of 20 chips. And really, I should say the proportion of peach, right? Because that's what we're counting, from one sample of 20 chips. How many Post-its are in this distribution? So I know if we go through and count that there are actually 47 if we counted these X's. So if we added up 1, 2, 3, 4, 5, 6, 789, if we got to here, right, if we added them all up, there are 47 Post-its. What does this represent? 47 samples were taken. Describe the shape of the distribution. I mean, it's a little bit, it's not perfect, but it's approximately mound shape. I don't have a big tail in one direction. So we're just going to say approximately mound shape. And in these lessons, we will kind of learn like, well, what can I do to get it more mound shape and different changes we can make. So it's approximately mound shape. And then our big question is the next one. We're going to give an estimated range that includes the middle 95% of the values. So if you remember, this 95% from our perfect normal curve went with plus or minus 2 standard deviations away. And we said stuff inside the middle 95% was expected and stuff outside the middle 95% is not expected. So the first thing we need to do, if we want the middle 95%, we're cutting off 5%. And that means we're cutting, I'm going to write this down here, 2.5% off each end or tail. Okay? So we need to cut some dots off each tail. We don't have a whole lot of dots or X's here. So when I do 0.025, 2.5% of the total 47, that ends up equaling, let me just grab a calculator quickly. It's not going to be a perfect number, and we're going to round it to the nearest whole number. So here we have 47 times 0.025. So that means I'm cutting 1.175 when we round to the nearest whole number. So 1 dot off each end. So I'm going to cut, this one is obvious. I'm just going to cut that off that end, cut this one off this end, and look at the remaining data. So the remaining data ranges from 0.25 to 0.55. So if I was going to take another sample from this population that has 40% peach chips, I would expect that number to be between 0.25 and 0.55. And specifically, so we'll look at this next question, if you were to take another sample of 20 chips, in what range of values would you expect or be 95% sure that the sample proportion would fall? So it has to be the same size sample as what we were doing. We were doing samples of 20. So we can use this data and we can say this is the expected values. Okay, and every single time, if this represented the population perfectly, we would get 0.40 because that's what the whole population has. But it doesn't, and it's a small sample. We'll talk about bigger samples are better in most cases in terms of narrowing that range. But we would, for the samples of 20, we would expect it to fall between those two numbers.